Welcome to this module where we are discussing state estimation. In today's lecture, we are going to discuss about Kalman filter. Specifically, we are going to do a derivation of the Kalman filter gain. This derivation is what is known as the least squares derivation. There is a more rigorous derivation that is based on the stochasticity of the overall system. We are not going to cover that. Okay, so let's go over the few definitions that we did in the previous lecture. X k plus 1 equal to axk plus buk plus epsilon k, and yk equal to cxk plus nu k. Okay, so this is the plant. We have done deterministic observer earlier, and deterministic observer is going to be x hat k plus 1 equal to a x hat k plus buk. This is just an open loop prediction equation, and plus, so yk minus c x hat k. This is the deterministic observer. What we are going to talk about is a stochastic observer. Okay, and one is a one-step prediction, and prediction equation is x hat k plus 1 given information up to time k is a x hat k at k plus buk. And filter correction is x hat k at k is going to be equal to x hat k at k minus 1 plus k multiplied by yk minus c x hat k at k minus 1. Okay, this can also be written as x hat k plus 1 at k plus 1 equal to x hat k plus 1 at k plus k multiplied by yk plus 1 minus cx hat k plus 1 at k. Both of these are equivalent. What we have done is just replaced k with k plus 1. Okay, few definitions. Okay, and the first definition was our error or filter error was defined as xk minus x hat k at k, and we had the one-step prediction error, that is xek was nothing but xk minus x hat k at k minus 1. Okay, so these were the definitions of ek and xek. We had also defined the covariance. Pk is expectation of E transpose Ek E transpose k. This was P, and we had P bar k as expectation of xek xe transpose k. Okay, note that so P and N, P bar are n cross n symmetric matrices. Okay. And I will also copy the plant equation. Okay, so let's take these two equations, subtract them, and what we are going to get is xk plus 1 minus x hat k plus 1 at k is going to be equal to a xk minus a x hat k given k plus buk minus buk. So these two will get cancelled, so I will just erase them out, and plus epsilon k, which then I can basically write this as xe k plus 1 equal to a ek plus epsilon k. Okay, so that's the first equation that I get. So xk equal to xk. I will just copy this. Okay, so minus this guy equal to minus this, move this over here, and minus this. Okay, the equation that we had over here. Yk was nothing but cxk plus nu k, and I'll just replace this yk with cxk plus nu k. This c and this c, I can take them common. K multiplied by c, and I will erase this c as well. Okay, so this is what I'm going to get, right? And I will take this nu out, and I will just have minus k nu. Okay, so this part is just going to be ek equal to xek minus kc multiplied by xek minus k times nu k, which is going to be equal to I minus kc. We have to post multiply it by xek, we cannot pre-multiply it, k multiplied by nu k. So this is ek. Okay, so these are the two equations that are important for us. So I'll highlight this. This is one and this is the other. Okay, so let me copy and paste it for our future derivation. See, this is one equation and this is the other equation. Remember, we also have the derivations that we had over here, and these are also important for us. We will highlight them in a different color. This is our planned, this is our prediction equation, and this is our filter equation. Okay, what we want to do is we want to find our Kalman gain k such that our error is minimized, our error ek or xek of course is minimized in some way. So the aim of Kalman filter, least squares derivation, find k such that error minimized in least squares sense. Okay, so we can do it in two ways. One is we can do it with a one-step prediction type, or we can look at it from a filter equation viewpoint. Okay, so either ways is fine. I will just copy and paste these over here, and I'll do the same for these as well. Okay, so these are the things that we have done so far. Okay, so let's take a pause and let's evaluate where we are. So the first equation is our plant equation. The second equation in red is our one-step prediction equation. The third equation in purple is our filter equation, that is using the measurements in order to correct our predictions. And the equations in yellow are how the overall errors are going to propagate in time. Okay, remember what we want to do is we want to minimize either XE transpose or E transpose. So we want to find K, minimize either. So find K, find KK to minimize either of these two options. Okay, that's the aim of our Kalman filter. So either of these are possible. So let's look at what XE is going to do. So we can write XEK, we can write it as A EK minus 1 plus epsilon K minus 1. Okay, P bar is nothing but expectation of XE transpose, which is expectation of AE plus epsilon transpose, which we can write it as expectation of AE transpose A transpose plus expectation of epsilon transpose plus expectation of AE epsilon transpose plus expectation of epsilon E transpose A transpose. Okay, this is what we get. We can take the A outside and we can take A transpose outside. Okay, and these guys are going to be 0. Why? Because epsilon is a white noise sequence. So we'll just delete these and we are going to get these guys. So this we can write it as A expectation of EK E transpose K, sorry, EK minus 1 E transpose K minus 1 plus expectation of epsilon transpose is nothing but R1. Sorry, I forgot A transpose over here. Okay, so this I can write it as P bar K is going to be equal to A P K minus 1 A transpose plus R1. Okay, now we can take this equation and we can write that as expectation of E transpose is going to be equal to expectation of I minus KC XE, okay, minus K nu multiplied by this transpose. Okay, and I will copy this in the next page. Okay, so this is our expectation. So this we can write it as I minus KC expectation of XE transpose I minus Kc transpose plus K expectation of mu transpose K transpose. We are ignoring the other terms because nu is a white noise and expectation of epsilon nu transpose is equal to 0. So based on that we are ignoring those terms. So let's not worry about those parts. Okay. So this I can write this guy as nothing but R2. So I will just replace R2 over here. And we have this overall equation. Okay, so this we can, and this is nothing but P bar. Okay, so Pk is going to be equal to I minus Kc P bar K I minus Kc transpose plus K R2 K transpose. Okay, so which we can write it as P bar plus K C P bar C transpose K transpose. So based on this and this we will get this term. Okay, based on this and this we will get this term. So these are the first two terms. The other term is going to be K C P bar. Okay, and the other term is going to be P bar C transpose K transpose plus K R2 K transpose. Okay, which we will be able to write this as P transpose, P is equal to P transpose. So we can write this as K multiplied by C P bar C transpose plus R2 multiplied by K transpose. Okay, minus I will write this as 2 P bar C transpose K transpose. Okay, so this is how I will write it. Not fully correct, but just taking a shortcut. So this is like our Hessian, this is our gradient. So based on that, if you want to minimize Kk is nothing but H inverse G. So therefore Kk is nothing but, now this is the Hessian, this is the gradient, and this is our result for Kalman filter. So this is the Kalman gain. Okay, and then we can substitute in Pk equal to P bar plus okay. If we were to substitute in this equation, again you can go over the math. The math is fairly straightforward. It's not too difficult. But when you go over this, what you will get is Pk is nothing but I minus Kkc multiplied by P bar K. Okay, so this is the equation that you will get. So I will highlight them. So this is one equation from the, this is the other equation, and the third equation is this guy. Okay, so these are the three equations which are important. I will copy this equation and I will paste it over here. Okay, so these three equations are the ones that are important from the derivation of Kalman filter. So let's complete the derivation. on the next page. Okay, this is what you can paste. I will delete this. Move this over here. Move this here. And move this over here. This is how the overall covariance matrices evolve with time and how the Kalman gain is calculated. Okay, and our k bar is nothing but a times kk. Okay, so this is what we are gonna get. Okay, so if we were to substitute basically our pk minus 1, basically this equation, if we were to substitute over here, we are going to get our p bar k is going to be equal to a multiplied by I minus kc multiplied by p bar a transpose plus r1, so which is equal to a p bar a transpose minus a kc p bar a transpose plus r1, and we can substitute the value of k from over here into this. So how will we do that? We will just move this onto this side. We will erase this and we will bring this part, duplicate and bring it over here. Actually, yeah, let me move this to this side. Okay, and this is our p bar k. So this, if you notice, is nothing but our discrete Riccati equation. Same Riccati equation that we had seen earlier in the LQR problems. Okay, so this is, so you can solve Riccati equation to obtain p bar infinity. From p bar infinity, once you know p bar infinity, so sorry, from once you know p bar infinity, you can calculate k infinity. So k infinity is going to be equal to c p infinity c transpose plus r2 inverse p bar infinity c transpose, and then you can then calculate p infinity, which is equal to I minus k infinity c multiplied by p bar infinity, and k bar infinity is nothing but a k infinity. Yeah, I'll just write this like this. This is what we are gonna get, and our p bar infinity and k infinity, p bar infinity and k bar infinity obtained from either DARE command, IDARE command, or Kalman command in MATLAB. Okay, so this completes the overall derivation of Kalman filter. Okay, so hopefully you have now got a hang of the overall derivation, and what we are gonna do is just look at the other parts, which is our x hat k plus 1, or rather x hat k given k minus 1 equal to a x hat k minus 1 given k minus 1 plus bu k minus 1. Okay, Then we have the calculations of calculate P bar k given k minus 1, then calculate calculate kk, then calculate p k at k, okay, and then you can get x hat k at k is going to be equal to x hat k at k minus 1 plus kk multiplied by okay. So these are the steps in calculating Kalman filter. Okay, so this is unsteady state Kalman filter. Steady state Kalman filter is, this is replaced by p bar infinity, this is replaced by k infinity, this is replaced by p infinity from IDARE or Kalman commands in MATLAB. Okay, so this is the overall steps that you can use in using Kalman filter. Okay, so with that I end this particular lecture. In the next lecture we will do a recap of all these steps as an algorithm that one needs to follow in order to implement Kalman filter. So that is the thing, that is the overall summary that I am going to present in the next lecture. So hopefully this particular derivation is clear to you, and thanks for listening, and I will see you in the next lecture. Bye.